Let's look at a few more examples on how to find a derivative function. We're going to first find a derivative function and then go ahead and find the equation of the tangent line at the point of tangency. This equation of the tangent line gives an illustration on how to tell whether the function is increasing or decreasing using the slope at a very specific moment. So here is a radical function. It is actually increasing from left to right, and it's also concave down, as you know from your graphing experience in algebra. But more importantly, from algebra, you realize the domain. What is the domain of the function here? It's actually x is greater than or equal to -2. Now, we'll go ahead and evaluate this limit. And it's good to write the definition of the derivative. The definition of a derivative is simply the evaluation of this limit. And if this limit exists, we will then have the derivative function. So we have to be patient here. We have to be persistent. We're just going to make a lot of substitutions. Whenever you see an x, you're going to replace it with x plus h. And now we're in an algebra scenario. Much of calculus is really about algebra. We're just going to use our algebra techniques, our algebra experience, react to certain situations, and manipulate them and simplify them in such a way where a lot of magic does take place. Keep simplifying. And you keep simplifying line by line, making sure you write the LIM notation. I am actually checking the form line by line in case you're wondering. Notice the numerator is becoming more and more magical. You'll see that there's only an h in the numerator. There's a common factor of an h in the denominator. So we'll go ahead and reduce those common factors. H over h is in fact 1. And if you've seen these difference quotients before, if you've seen the simplification of difference quotients, please be aware that you've had a decent algebra teacher. Now, if you check the form now, if you check the form of the numerator and the denominator, you'll realize you will have a determinate form. Just remember that h is your variable. You're looking at h approaching 0. This does simplify into a function in terms of x. And notice the domain here. The domain here is x greater than -2. So very similar to the domain of the original function, it only differs by an endpoint. Notice we can't equal -2 this time. That is the derivative function. Why don't I write it right here? I'll put a period here. I'll circle the very first sentence. And this very first sentence is going to support your second sentence. Therefore, the derivative function is what? It's 1 over 2 times the square root of x plus 2. Now let's look at the equation of the tangent line at the point of tangency. So part B, we got to figure out what a f of a is. Just by inspection, you'll see that a f of a is that ordered pair. Now, what is the tangent line? I should say, what is the slope of the tangent line? That is really the derivative evaluated at 8. And if you feel like rationalizing this, feel free. So there's the slope, and then we have the ordered pair. So one more procedure here. We have the slope, and we have the ordered pair. So we're going to use point slope formula to get an equation of the tangent line in the form of y equals mx plus b. And feel free to simplify this. And notice the equation of the tangent line is this. And you're done. Since the slope is positive at the point of tangency, we know that this function is actually increasing when x is equal to 8. Let's look at another example to see how the algebra could be a little different. Once again, we're going to write the definition. We're going to try to evaluate this limit in terms of x. X is a variable here. X is not a constant. We're looking for a function in terms of x. Whenever you see an x, you're going to replace it with x plus h. And we'll go ahead and evaluate this with common denominator. But instead of dividing by h, I am going to change the algebra a little bit. I'm going to multiply by 1 over h. And this will make it a little bit easier to read. We're going to now multiply by a conjugate. We're going to multiply by the conjugate of the numerator. And we just keep simplifying. We just keep taking advantage of our knowledge of algebra. Much of calculus is just knowledge of algebra. Notice the numerator is simply the opposite of h. And if you had done this in an algebra class before, you've had a decent algebra teacher. Notice we finally arrived at a determinate form. And if we arrived at a determinate form, we're ready to evaluate this limit. Remember, h is your variable here. And so when you plug in h here, this does simplify. This will simplify into a function in terms of x. And put a period there. That is my first sentence. My second sentence is actually declaring that the derivative function in function notation, it's equal to this. Make sure you write the function notation. That's very important in calculus. We want to make sure this is different from our f of x function. Notice the domain of the f of x function was x greater than 0. And notice the domain here for our derivative function is also x greater than 0. Let's look at the slope, I should say, let's look at the tangent line at the point of tangency. So what is a f of a? A f of a is simply 1/4, comma 2. And can we get the slope? Well, yeah, the slope of the tangent line is really the derivative evaluated at 1/4. So what is the slope of the tangent line evaluated at 1/4? We get 4. Now we're ready to use the point slope formula. And simplifying this, we'll get the equation of the tangent line in y equals mx plus b form. Notice the variable here is x and the variable here is y. So there's only two variables, it's x and y. And go ahead and simplify this to get it in y equals mx plus b form.